Bismillahirrahmanirrahim. Welcome everyone. And today we are going to start the next topic of the chapter gases, and it is about the liquefaction of gases. Liquefaction of gases simply means that you want to convert a gaseous substance into its liquid state. So liquefaction means that the conversion of a gas into its liquid state. Now you know that gases have very weak intermolecular forces. While liquid state, as compared to gaseous state of a substance, that has stronger intermolecular forces. So basically, if you want to change a gas into its liquid state, then you will have to convert the weaker intermolecular forces into the stronger one, or you will have to make the intermolecular forces stronger. In order to make the intermolecular forces stronger, you will have to do two things. The molecules must be moved closer to each other, and secondly, the molecules must be slowed down. When the molecule come close to each other and even they are slowed down, then the intermolecular forces they become stronger. Now molecules can be made close to each other by increasing pressure or by the compression of the gas, and molecules can be slowed down by decreasing temperature of the gas. So if you want to convert a gas into its liquid state, then you will have to compress it and you will have to cool it down. It is very important to note that when we studied the isotherms of a gas at different temperatures, isotherm, let me remind you, it is the graph of the Boyle's law. So when we studied isotherm of a gas at different temperatures, we came across a term that is called as the critical temperature of gas. Critical temperature of a gas is actually the temperature above which a gas can never be liquefied, no matter how much pressure you apply on it. So first of all, you will have to achieve the critical temperature of the gas, and then you will apply a certain amount of pressure, a certain quantity of the pressure against it in order to convert the gas into the liquid state. Critical temperature is the highest temperature at which any substance may exist in. It is a very important MCQ. Alpha as gas, beta as liquid, Charlie as solid, and delta as plasma. So critical temperature is the highest temperature at which a substance may exist in its which state. So the correct answer is the liquid state. So critical temperature is the highest temperature at which a substance exists in the liquid state. If the temperature will be greater than critical temperature, then the substance will not be in its liquid state, but it will become a gas again. Now, the pressure which is applied against the critical temperature to convert a gas into its liquid state, that is called as the critical pressure. It is actually the minimum pressure which must be applied against the critical temperature to convert a gas into its liquid state. And there is a third term, that the volume of a 1 mole of a gas at its critical temperature and critical pressure, that is called as the critical volume of gas. So critical temperature is the temperature above which a gas can never be liquefied, no matter how much pressure is applied. The minimum amount of the pressure which must be applied at the critical temperature to convert a gas into its liquid state is called as critical pressure, and the volume of 1 mole of a gas at its critical temperature and critical pressure is called as critical volume. And these three parameters, critical temperature, critical pressure, and critical volume, they are collectively called as the critical constants of a gas. Now let me tell you a very important thing, that there are two types of the gases. One are the polar gases and other are the non-polar gases. For example, among polar gas, we may take the example of ammonia, and against a non-polar gas, we can take example of carbon dioxide. The comparison of their critical temperature will provide us a very important information. You must have an idea that the critical temperature of the ammonia is 132.44 degrees, and the critical temperature of the carbon dioxide is 31.24 degrees C. Now you can see that the critical temperature of a polar gas is greater than critical temperature of a non-polar gas, and usually this is a routine, that the critical temperature of the polar gases, they are greater than the critical temperature of the non-polar gases. Why? Because the polar gases have stronger intermolecular forces, and these intermolecular forces may be the dipole-dipole forces, or particularly in case of ammonia, that may be the hydrogen bonding. While in non-polar gases there are weaker intermolecular forces, and the prominent intermolecular force in the non-polar gases is the Linde dispersion force. So the comparison of their critical temperature tells us that polar gases can be more easily liquefied as compared to the non-polar gases. Mean you will have to cool the non-polar gas to a much lower temperature in order to liquefy it as compared to the polar gas. It means that polarity makes liquefaction easier. And keep one thing in your mind, that a gas having the stronger intermolecular forces is actually a more non-ideal gas, while a gas having weaker intermolecular forces is relatively an ideal gas. So you can also say that it is easier to liquefy the non-ideal gases as compared to a comparatively more ideal gas. And keep one thing in your mind, that the perfect gases or 100% ideal gases, they cannot be liquefied because of the absence of intermolecular forces in them. But these gases do not exist. There are certain gases which are very close to the ideality, especially at high temperature and low pressure, but even then they can be liquefied if their critical temperature is achieved. So we can also say that non-ideality is directly proportional to critical temperature, is directly proportional to easiness of liquefaction of gas. So a gas which is more non-ideal has always higher critical temperature. Mean that gas does not need to be cooled down to a greater extent in order to convert it into the liquid state. So the non-ideal gases have high critical temperature, and all those gases that have high critical temperature, it simply means that they can be easily liquefied. Now a question arises in our mind, is there any method by which the gases can be liquefied experimentally? So a method which is very commonly discussed in the books, which is used to convert a gas experimentally into its liquid state, is the Linde's method of liquefaction of gases. And what is the principle of the Linde's method of liquefaction of the gases? That is a Joule-Thomson effect. What is Joule-Thomson effect? According to this effect, when a highly compressed gas is suddenly allowed to expand in a region of low pressure, it causes cooling. Actually, when a gas is compressed, listen very carefully. When a gas is compressed, the intermolecular forces in the gas, they become prominent, they become stronger. And when the gas is suddenly allowed to expand into the region of low pressure, the molecules, they try to move away from each other. But in order to move away from each other, the molecules will have to overcome the intermolecular forces created by the compression of the gas. And in order to overcome the intermolecular forces, the gas molecule use some of their own kinetic energy, due to which the gas cools down. This is the Joule-Thomson effect, and it is the base of the Linde's method. Now let us discuss what is the apparatus which is used in the Linde's method and how the Linde's method works. This one is a compressor which will compress the gas, and the gas to be liquefied is introduced into it. Suppose that we want to liquefy air, so the air will be introduced into the compressor. Normally the pressure of air is 1 atm and compressor compresses it to 200 atm. Now the air will be in the highly compressed form. And when this compression takes place, as a result of this compression, the intermolecular forces, they become stronger. And you know the formation of forces, whether intermolecular or intramolecular, that is an exothermic process. So during this compression, some of the heat is released which makes the air hotter. This is called as the heat of compression. Now the air becomes hot when it is compressed in this compressor. So that air is passed through a pipe, and this pipe has a refrigeration liquid, a refrigerating liquid here, refrigeration liquid, and you must have an idea, please note it down, that for the refrigeration, the liquid which is used, it is a very commonly found liquid, like the chlorofluorohydrocarbons can be used, ammonia can be used, propane can also be used for this purpose. Now this hot air passes through this pipe or this tube, and as the hot air passes through this tube, the refrigeration liquid, it makes this hot air cold again by extracting the heat of compression out of it. So this cool down air now moves to this box, and this tube ends in the form of a spiral pipe. Now why this pipe is made as spiral? Because we want the slow expansion of the gas. So the spiral pathway makes the molecule slower and the expansion will also be slower. When the air moves through this spiral pipe out here, it is suddenly expanded. So the highly compressed air is suddenly expanded into the region of low pressure. What will it cause? According to the Joule-Thomson effect, it will cause cooling. And this chamber cools down. The air is recircled again to the compressor, and this process is repeated again and again until this chamber is so much cooled that the critical temperature of the air is achieved. And as the critical temperature of the air is achieved, the air is converted into its liquid form, and the liquid air is collected here. And the air which is not converted to the liquid, it is again processed through this again and again. And this liquid air has light blue color. Now, all the gases can be liquefied by this process, in which the highly compressed gas is suddenly allowed into the region of low pressure. According to the Joule-Thomson effect, it causes cooling, and this cooling achieves the critical temperature of the gas to be liquefied. All the gases can be liquefied by this technique except two gases. This is very important point. And these two gases are helium and hydrogen. Why these cannot be liquefied by Linde's method? Because of their very low critical temperature, which in turn is due to their very small size and their non-polar nature. Now the very small size of the helium and hydrogen molecules and very weak intermolecular forces, that makes them very difficult to be liquefied, and that decreases their critical temperature very close to the absolute zero. The critical temperature of the helium, I have noted that it is almost 5.19 Kelvin, or you may say it is minus 267.96 degrees. And that of hydrogen, it is 33.2 Kelvin, which is equal to minus 239.95 degrees. You can see that their critical temperatures, they are very low, and that's why these gases are very close to the ideality, because the intermolecular forces are very weak in them. And this low critical temperature of minus 267.96 minus 239.95, this very low critical temperature cannot be achieved using the Linde's method of liquefaction. So Linde's method cannot liquefy the hydrogen and helium, and all other gases they can be liquefied by this process. This was all about the liquefaction of the gases. Please listen this lecture very carefully and try to learn out of it. Thank you so much. Allah Hafiz.